Hey, what is new with you fellows? I'm Ayub and I'm here today to talk about the microkernel architectural pattern. This is one of my favorite patterns and I just love it. So let me tell you about it a little bit. In this video lesson, we're going to start off by discovering the origins of this pattern, and it won't be a history section. It will put us in context and equip us with basic concepts that will help us understand the pattern better. After that, we will dissect the pattern and discuss it in details. And this will be followed by examples and use cases of this pattern. Next, we will evaluate the microkernel pattern and view it from the pros and cons perspective. This will help us in evaluating the trade-offs of this pattern and allow us to make better decisions. We will also talk about some important considerations regarding microkernel systems, and I will conclude by listing some good resources to learn more and suggesting where you could go from there. Okay, let's dive in already. The word microkernel includes the term kernel, which originally means the nucleus or the core part of something. In computer science, it denotes the part of the operating system that directly controls the hardware and manages the available computer resources. And so far, we know that this term first appeared in the context of operating systems to refer to the core and essential part of an operating system. This kernel is further extended and enhanced by integrating and adding new and custom functionalities and services, usually in the form of layers and extensions through its API. And eventually, we get a full-fledged operating system. Over time, different variants of this concept appeared in the area of operating systems. Two important kinds were the microkernel and the monolithic kernel. In general, they both represent the core of the operating system, and both of them manage computer resources and provide basic operating system services. The only difference is that in the microkernel approach, which appeared in around the early 80s, the core of the operating system is smaller and more efficient. More specifically, the user services and the kernel services are implemented in different address spaces, and the kernel is kept to a minimum comprising only services that manage process and memory. Whereas in the monolithic kernel, all services including user services are implemented in the same address space. This makes the core of the operating system bigger in size and less flexible. This doesn't mean, of course, if we use the microkernel approach, those services won't exist. It means that they are separate from the core and we have some sort of flexibility into choosing what services to implement, change, eliminate, or do whatever we want. As long as we have a well-defined core API, we can extend the core and customize the operating system as needed. The good news is that these concepts and the principles of such approach are not restricted in the context of operating systems development only. This approach, which became an architectural pattern over time, proved to be very effective in building software applications, and now, with the revolution of distributed computing, it became a good blueprint for some types of web-based systems. I want to conclude this section with a simple fact. The microkernel approach in operating systems appeared out of the need to add custom services to the operating system without having to modify a large portion of the system. It's made it easy to build operating systems for special computers, and also it solved the problem that was common in a monolithic kernel. This issue was that when a service in the kernel failed, often it led to the failure of the whole operating system. Keeping these two pieces of information in mind will help in understanding the rest of the video, and also will allow us to appreciate this pattern and the problems it solves. Alright, let's take a closer look into this architectural pattern and see how it is implemented in the context of software and web applications. And before I proceed, I want to include an extract from the famous book of pattern-oriented software architecture that would help us place the new information in its right place. The microkernel architectural pattern applies to software systems that must be able to adapt to changing system requirements. It separates a minimal functional core from extended functionality and customer-specific parts. The microkernel also serves as a socket for plugging in these extensions and coordinating their collaboration. Now, let's continue, and as we do so, this explanation will make more sense and everything will fall into its right place. As always, let's start by defining the major components in this architectural pattern. My simple version of the anatomy of this pattern is that it consists of two major components, the core and the extensions. But the more detailed and precise version is that it consists of five main elements: the core, internal servers, external servers, the adapter, and clients. The four different elements in this version are different kinds of extensions, if you will. Now let's dive deeper and go through each element one at a time. And as a note here, I'll be using both versions, the simple one and the detailed one in my explanation, not interchangeably, but whenever one is appropriate. Okay, the core, or the microkernel component. The core system consists of the functional and operation code that is necessary for the application to run. It contains the minimum set of functions for the system to be operational, meaning that it is the code that gets executed every time the system is used. This element takes the form of a monolithic mini application. In some cases, the core system is a layered application that exists in one place. And because the core component in this pattern provides a plugin mechanism that gives the developer and the system as a whole some sort of flexibility in terms of what functionality is provided to the user. Because of this, the core component will include, in addition to basic services, code, functionality, and mechanisms for coordinating and managing the collaboration of the various plugged modules. Also, and especially in web-based systems that are built using the microkernel approach, which means oftentimes plugins will be distributed and will run in separate processes. Because of this, the core system needs to have a mechanism to check the availability and responsiveness of the plugins. Or if we want to talk in terms of the second version, the availability and responsiveness of the internal servers. Alright, now I said earlier that I refer to the four elements as extensions. But are they different from each other? Yes. The first type of extensions are internal servers. Internal servers are directly related to the core. Remember that the core should be kept to a minimum, so that when it is shared among different applications or for coordination purposes, it will maintain its performance. If the system requires more core functionality than the microkernel should contain, we move to internal servers. Okay, we implement the additional functionality of the system through internal servers on separate processes. And now we could see the core and the internal servers as one entity that comprise the basic functionality of the system. These servers may operate independently with the core or may have to interoperate. In the latter case, the core will handle their coordination. This has several other benefits in addition to the main advantage I mentioned earlier: flexibility, portability, and ease of maintenance, to name but a few. Internal servers could exist on the same computer or be distributed over a network. And of course, internal servers are used by the microkernel whenever needed. Alright, external servers are another type of extensions, but they are quite different from internal servers. External servers are the last part or the outer layer of the backend system. These extensions or servers are abstractions over the microkernel and they implement their own business logic over it. In other words, we could use the same core and internal servers for different but similar application domains, but the external servers will differ depending on the application domain. For example, in financial technology or banking systems, different enterprises with different policies could use the same core, that is to say the same microkernel plus internal servers, but different external servers that implement different abstractions and business logic. And so external servers are used to build or create different versions of the system. Okay, external servers also run on separate processes and expose their functionality through an API. Alright, let's move to clients now. Clients, well, are clients. Such components are external to the system and they seek its functionality through external servers. A client is associated with only one external server, and it communicates with it through an adapter which serves as a middleware or as an API gateway in Microservices system. We use an adapter to avoid tight coupling. The job of an adapter is to forward client requests, hide complexities, and avoid the need for the client to change as the external server's functionality and API change. And an adapter is not required for such systems, but it is preferable. We will address that once again in the variants section. Alright, I hope I've presented a clear idea about the internals of the microkernel system, and this should be enough to put you on track. And here is again the previous diagram that sums everything we went through in a visual form. It's easier to remember it this way, or not. Okay, now let's see a microkernel system in action. When a microkernel system is involved, a typical client-server interaction goes like this. First, the client calls the system requesting a service, then the adapter receives the call, does something with it if required, and forwards the call to the microkernel. Since the microkernel handles the communication and coordination side of the story, it fetches the address of the necessary external server and sends it back to the adapter. The adapter then establishes a connection between the client and the external server by sending the appropriate request to the server through a REST call. After receiving the request, the external server analyzes the request, prepares the answer, and sends it back upon completion. And finally, the adapter sends back the response to the client, and bam, we we have a happy client. That is if the response is what the client was waiting for, of course. Alright, so we barely scratched the surface here with this simple walkthrough. There are a lot of complexities under the hood, such as whether the functionality required by the external server to fulfill the request is provided by the microkernel or the internal servers. But of course, eventually it all boils down and everything is based on proper communication and coordination. Alright, we've already mentioned examples of systems built using this approach. Operating systems, which are the birthplace of this architectural pattern. Another example are databases and financial applications, as we've explained earlier. Also, there are quite a few types of software systems that are good candidates for this pattern, such as IDEs, text editors, as well as web browsers. The microkernel pattern is generally the default solution for applications and platforms that must cope with continuous hardware and software evolution. For this reason, we don't see a large number of existing operating systems. Systems built using this pattern are designed to last for long and adapt quickly to keep up with the fast technological advancements. Also, another type of systems that are most likely to use this architectural pattern are applications that need to integrate with and embrace existing standards and interoperate with systems that already follow standards. Not only that, such systems are highly flexible and fast at adopting new standards. Also, usually the microkernel is the default solution for software product lines, and essentially this type refers to a set of software line systems that share a common managed set of features satisfying a particular market or mission area. Such systems are built from a common set of core assets in a prescribed way. In other words, the microkernel pattern is used to develop similar but different software applications that are built off the same core platform. The resulting products are similar in their core but different in the features and functionality. It's worth noting that it is up to the developers and engineers to decide what functionality should be part of the core system, that is to say the microkernel, and what functionality is to take the form of an extension or an internal server. Other systems that may be built using this architectural pattern are highly customized products, software platforms that would be the foundation upon which more sophisticated and customized systems, platforms and applications that are likely to have many different flavors and versions, etc. Probably the most important skill a software architect could have is the adeptness at evaluating trade-offs of a particular architectural pattern through the analysis of its benefits and limitations. As I say in each architectural pattern video, this allows us to make the right decision and design the system the right way and help us avoid the dead end. Okay, we've already mentioned some of the strengths of the microkernel pattern. Let's add some more and see some limitations of this pattern so that we can have a complete picture. Alright, one of the obvious advantages in systems built using the microkernel architectural pattern is extensibility. This is thanks to the ability and ease of integrating and extending the system with new internal servers. Another benefit is the agility of the system. Through the separation of the low-level mechanisms of the system, which are represented by the core, and the high-level features and services, the overall agility and responsiveness as well as maintainability will improve as a result. Of course, ease of development and maintenance of the system is another advantage, and that is because adding and removing functionality is just a matter of plugging and unplugging small self-contained and independent modules. Also, because most of the functionalities will be provided by internal servers and abstractions of the core will be achieved through external servers, which could be tested and validated in isolation, we could consider ease of testing another gain if we are to use this pattern. And last but not least, and this is my favorite, portability. This is apparent in all the examples we've mentioned before. If we are to use the software in a totally different environment, especially in terms of hardware, only the microkernel or the core needs to be changed to accommodate to the new environment. Another thing I want to add here is that one of the important things the core component does is that it usually abstracts away the environment's specific variables and characteristics. This is especially true of operating systems. These are all good benefits that could be reasons to use the microkernel architectural pattern. But there are actually things that this pattern does not excel at, and here are some. Due to the nature of this architectural pattern, there would be a lot of inter-process communication in such software systems. Complexity is another issue here, and that is because the design and implementation of robust systems is complex than the design and development of monolithic applications. And lastly, scalability is difficult in such systems due to the nature of the core. However, scalability is easier at the extension level. There could be other disadvantages, but these are the main ones when it comes to the microkernel architectural pattern. Alright, when implementing architectural patterns, it's easy to derail from the right track by falling into traps and pitfalls. Or one can be in the right track, but the pattern seems to be difficult to implement. Here are a couple of things to keep in mind. Patterns can be composed. Yes, that's right. You can find a system that uses more than pattern to achieve its end goal. In fact, almost invariably, large-scale systems in some of the good software products out there are hybrid systems. If you've decided that what the microkernel provides is what you're looking for and still find it difficult to build your software using this pattern, it's most likely only part of your application will need to be built using the microkernel pattern. Another thing to keep in mind is that there is some sort of freedom into choosing the messaging mechanism for the system, especially between the core and internal servers. Choosing the right approach depends on the application and also the quality attributes of the whole system. Contract versioning is really important. Extensions will be added, maintained, updated, and removed frequently, and it's possible to have more than one entity and third parties developing the extension. And finally, using an adapter would be necessary for third parties and to abstract away dealing with different contracts and to hide complexities and message transformation. Okay, these are some of the important considerations one needs to keep in mind when building microkernel software systems. Alright, for this video lesson, I only have one resource and one step to make if you want to understand the philosophy behind the microkernel pattern and architectural patterns in general. Pattern-oriented software architecture, a system of patterns. This book is a really valuable book, and I mentioned it in the software architecture video. It equips the reader with the knowledge one needs to understand and grasp the philosophy behind patterns and even create custom ones for special scenarios. I hope by now you have a fair idea of the microkernel pattern and understand the basic concepts and hopefully can explain them to others. Alright, I hope you enjoyed this video. Please don't forget to subscribe and hit the bell icon. Till the next video, stay tuned.